You can see by the highlighted dot point there that we're looking at particle interactions using Feynman diagrams. There are actually only three interactions that you need to be able to interpret from a Feynman diagram. But we'll first of all just mention what Feynman diagrams are. They are a graphical representation of particle interactions. And when we say graphical, we mean a graph. A graph representing the way that particles interact. And it helps just to make a little bit more sense of what's going on with the particle interactions. It may also confuse you when you first have a look at it. There are a few odd things about it, but once you get the hang of it, it does seem to make a fair bit of sense. There are a few conventions that we're going to use when we look at these Feynman diagrams, so I'm going to go through them now. As we do this, I'll include a graph on the right hand side to show all these aspects as we go through. The first thing is that the horizontal axis of this graph represents time, and the vertical axis will represent space. Be aware that if you do go looking up any other Feynman diagrams, that sometimes is reversed, but in the syllabus it very clearly identifies that the convention we're going to use is time on the horizontal axis and space on the vertical axis. So that's what the grid looks like there. The second is that particles are represented by straight line arrows. So that means that we're going to have a straight line with an arrow on it to indicate the particle, and importantly the arrow is in the direction of time. And in order to make it clear what the particle is, there's also going to be labels. So that indicates the type of particle. And so in this example we have an electron represented. We also have antiparticles that need to be represented, and so they're a little bit back to front. So antiparticles are basically the same, except that their arrows are represented in the reverse direction. So they're still represented as straight line arrows, but now the arrows are in the opposite direction to time. So that's to indicate that they're antiparticles. It doesn't indicate that they're moving that direction in time. It's simply a convention to show that they're an antiparticle. And continuing the example, here we have positron represented. The next one is about bosons. They're represented as wiggly lines, and yes, that's the technical term that we're meant to use, and they will also be labelled to indicate the type of boson. And in this interaction between an electron and a positron, it would be governed by a photon, given that it's an electromagnetic force that exists between those two particles. The last important point is that at each vertex, and by vertex what we mean is this point here, so where particles are actually coming into contact, I suppose, or interacting directly, there are a few things that are going to be conserved. Those things being charge, lepton number, and baryon number. So they are all conserved. So we can see then in this interaction that in order for charge to be conserved, we need to have an electron coming off the top, given that a photon isn't charged, and likewise we'd have to have a positron coming off the bottom vertex. This interaction is actually known as bar-bar scattering, and it's one of the interactions that we need to represent carefully. So let's now go and have a look at all of those interactions that you actually need to be able to reproduce. So first of all, we have an electron and an electron. Looking at the Feynman diagram that we would need to produce there, we can see again space on the vertical axis, time on the horizontal axis. So here we have an electron. It's going to interact with a second electron. The boson that will mediate that electromagnetic interaction is the photon, and we'll then see that the electrons are then repelled, and so they continue on as electrons. You can see there that the charge is conserved and lepton numbers conserved at each vertex. The second example is an electron and a positron. And as we saw in the example earlier, we had bar-bar scattering, so I'll just reproduce that again here. And we also have another interaction that can be represented for an electron and positron. So if we start out with the electron and the positron interacting directly with it, they'll annihilate each other to produce a photon, and then shortly after that the photon will then be able to pair produce an electron and a positron. That idea of pair production is not anything you need to know in any more detail than what's represented on this graph. And finally, the last one that we need to cover is a neutron decaying into a proton. And we also know that when the proton is produced, an electron and an electron antineutrino are produced. So again, if we start with our axes, here we have the neutron. Note that we don't have any other particles interacting here because the neutron is decaying. We know that a proton is produced, so we can draw that in. Notice now that the charge needs to be balanced, and so the boson that will be mediating this interaction is going to be the W negative. So that will balance the charge from the proton. And then from the W negative boson, we'll also see the production of the electron and the electron antineutrino. There is a second representation that you need to be aware of here, and that's using the quarks that are contained within the neutron and the proton. I'll just show that graph rather than showing the steps. You may recall that the neutron is 2 downs and an up quark, whereas the proton is 2 ups and a down. So you can see in this top line, the up quark remains unchanged, and in the second line, the down quark remains unchanged. It's the second down quark that actually turns into an up quark in the decay of the neutron into a proton. So there's the representation using the quarks that are contained within those two baryons. So there's the interactions that you need to know. Make sure that you can interpret them, make sure that you can understand them. It does take a little bit of making sense of how to reproduce them and how to draw them. I'm not sure if you will need to draw them from scratch or if you'll just need to be able to interpret them. So make sure you do have a good understanding of those representations.